All right, so now it's foam as a granular material.
Thank you. So I'm not going to talk about grains, but about foams, even if I'm going to pretend that they are just a particular type of granular material. This is something we've done in Dublin with Stefan Hötzler and Dennis Weir. And as you can see, it's pretty intuitive that it behaves somehow like grains. It's made out of bubbles instead of sand grains, but it can flow here. It can be stiff as a solid there. Yet this is not the usual way foam people look at a foam. They usually consider a foam as a network of soap films, as you can see here, or as a network of plateau borders, which are the little channels here where all the water is. It looks a bit complicated in 3D, but in 2D it looks very simple. And if you manage to remove all the water, you end up with this simulation. Basically, the foam reduces to a polygonal structure where everything is controlled by the three plateau rules and by the Laplace law, depending on the pressure differences. So when you have this ideal mathematical foam, if you want to know how it moves, you just perform simulations that are based on the minimization of the surface energy. So you typically use this surface evolver program. It's pretty time consuming, but it works pretty well. The problem is that if you want to go to dynamical regimes, you don't have any dissipation inside something like this. So if you want to see grains, you would like to add some water. And if you increase the liquid fraction of the foam, at some point the bubbles will become roughly spherical instead of being polyhedral, or in this case they would be polygonal. And we would like to know whether it's useful to treat them as if it was a granular material and whether or not they behave like sand grains. So I'm only going to talk about 2D foams, and these 2D foams are a bit confusing because you can change different kind of setups. You can either suppress the purely 2D foam as this one. You just have bubbles floating on top of a liquid, so you don't have any perturbation, any wall effect. Then you can add a glass plate on top of that, or you can squeeze your bubbles between two glass plates. So we'll see that this can have some effects on how the foam behaves. So now you can basically, once you've said that the bubbles are like grains, you can do with bubbles everything that you would do with grains. That's, for instance, what Jan Berthaud, who's here, has done with Nicolas van der Waal. They built some kind of an upside-down hourglass with the bubbles flowing upwards through a small hole here. And they found that the relation between the flow rate and the diameter of the hole looks like some kind of Bevelow's law for grains with different exponents. In Dublin with Wipke Drunken, we tried to put a monolayer of bubbles in some kind of a rotating drum. It's a bit complicated because, of course, if the drum is vertical, all the water will flow downwards, and we won't have grains anymore. We'll find polyhedral bubbles. So if you slightly incline the rotating drum, you can do things like trying to mix, I don't know if you can see clearly here, small bubbles here, big bubbles there. And as you rotate the drum, instead of segregating like grains, they will perfectly mix in the drum. I won't go into any details about that. I'll talk mainly about this experiment that was done first by Georges de Brejas in 2001. It's also an experiment that's been done with grains. They took either a dry foam here or a wet foam there, squeezed it between two glass plates, and between two cylinders. They rotate the inner cylinder, and they measure the velocity profile through the sample. They realized that only a few layers of bubbles on the moving wall were moving, so the flow is completely localized here. The velocity profile is exponential, so there is some shear bending in this setup. Then the group of Mike Denin reproduced this experiment with an easier geometry, with a simple shear, so they just shear like that. And they try it with a different kind of two-dimensional foam first, with bubbles floating at the surface, bubble raft, and then with a glass plate. and they realized that if the shear rate is uniform, so in a linear geometry, if you don't have the glass plate, you don't have any shear bands. If you add the glass plate, you have some shear band. And they found that the width of the shear band is independent of the driving speed of the setup. So all of this was quite nicely reproduced by a small continuum model that was developed in Dublin by Eric Janot, that was based on a simple Bingham rheology, which is often used to model the behavior of the foam. Problem is, in 2008, the group of Martin van Ecke in Leiden reproduced again the experiment, basically in all possible geometries, but with polydispersed foam instead of monodispersed foam. And non-intuitively it changed everything, and the width of the shear band was now depending on the velocity. The faster you move and the narrower the shear band is. So to understand the influence of something like the polydispersity, we need more than a continuum model, we need a discrete model. And there was a discrete model that had been proposed by Dugdurian in 1995. He basically said that a wet foam was just a packing, in 2D was just a packing of soft disks that can overlap. He did some traditional molecular dynamics with a completely negligible inertia. And since he was more interested in the quasi-static properties and not really in the rheology, he chose to apply a mean field approximation. And he ended up finding a Bingham rheology, which is the one that was also used in the model. So we wanted to try to do the same, but to add the effect of the glass plate to see if we could reproduce the formation of the shear bands, and without this mean field approximation, because we want to go fast. So the ingredients of his model were very simple. You have two bubbles colliding. Instead of deforming, they will just overlap, and they are pretty soft, so they can overlap by even more than 10 or 20%. He chose to take a linear elastic repulsion between the two bubbles. That's just due to the surface tension. It's not exactly what we should adopt, because some calculation on droplets have shown that it's not exactly elastic, and it shouldn't even be completely additive. The force should depend on the number of neighbors you have, but still it's a reasonable approximation. Then if the two bubbles are sliding along each other, they will experience some viscous dissipation. There will be a thin film between the two bubbles, and of course energy will be dissipated here by viscosity. Durian once again took linear force here, which is a bit more annoying. The problem of knowing how energy will be dissipated when two bubbles are sliding along each other is quite complicated. Even when you have only one bubble sliding along a gas plate, it's complicated. It's not linear. It had been treated by Bretherton in the 60s. He showed that the force scaled like the velocity to the power 2/3, even if everything is Newtonian, just because the geometry of the contact between the bubble and the plate is not trivial at all, and all the dissipation will happen in a very small region here. And it's been confirmed both experimentally and numerically, but it's also been observed that if you change the properties of the surfactant, which is what physicists never want to do, but the chemists like Nikolai Denkoff always want to change the nature of the surfactant, you can change the surface viscosity of these molecules. And depending on the surface viscosity, the force will either scale like v to the power 2/3 or v to the power 1/2, or anything between these two extreme values. Then if you have the more complicated situation of having two bubbles instead of one bubble in a solid wall, we can just expect that it will have roughly the same behavior. It's being done at the moment these days by Nikolai Denkoff. Anyway, it shouldn't be 1, it should be 1/2 or 2/3 or anything between these, but we'll start with 1 and see what happens, and then we'll see what, with other values. So here's what we do on a small sample just to see what happens. Just bubbles, polydispersed foam. They can slide very easily along each other. We just impose the speed here, and we measure the stresses on the boundary here. The velocity profile will be linear in average. We still don't have any glass plate, so there's no shear bands. And we want to know the rheology of that material. Here I've plotted the tangential stress as a function of the dimensionless shear rate And you can see that it's the numerical points are the black dots here. The Bingham fit is here, so the Bingham fit doesn't really fit. And it looks more like a Herschel-Berkeley rheology. That is, the stress is equal to a yield stress. There's a threshold that you need to overcome to start to flow. And then there's a term that's proportional to the shear rate to a certain power, and this power is 0.54, so roughly 1/2. So even if all the local ingredients were linear in this case, the collective behavior is not linear anymore. And it's actually not that bad because the experimental values are far from a Bingham fluid as well. The problem is that it's quite complicated to measure. I just show you 3 different experiments, very recent ones, and we already have 6 values of this Herschel-Berkeley index. Denin found something between 1/3 and 0.45. Denkov showed that it's a different value depending on the nature of the surfactant, between 1/4 and 0.42. And the group of Leiden, of Martin von Ecke, showed that it depends on the polydispersity. Polydisperse 0.36, monodisperse 0.6. So we're in the right range. We're maybe a bit too high, but we were hoping that by changing the local properties, it would change the Herschel-Berkeley index. Didn't really work. We wanted to try to vary all the local properties. The liquid fraction, which is basically how much we compress the bubbles between the two edges, doesn't play any role in the Herschel-Berkeley index. It will just modify the yield stress, but not the power law. The polydispersity does play a role, and of course, if it's monodisperse, you will tend to have nice lanes of bubbles sliding on top of each other, and it would logically be the exponent you put locally. But we're still working on understanding how it goes from monodisperse to polydisperse. Then we changed the exponent for the local repulsive force. It doesn't change anything. And for the local friction force, which also doesn't change anything. So whether you take 1/2 or 2/3 like you should do, or you take 1, it always gives 0.5 something. So it proves that this value of the Herschel-Berkeley index is quite robust. It doesn't depend on anything. But then we don't understand anymore why Denkov observed that the rheology depends on the surfactant properties. Then we also measured the normal stress. The normal stress follows the same kind of law. It's equal to pi naught, which would be what is called the osmotic pressure of the foam, plus a term that once again is varying like the shear rate to a given power, 0.4, which means that a foam, just like sand, has a tendency to expand its volume when sheared. So it's exactly like for grains, there's a dynamic dilatancy. It had been predicted already theoretically that there is a static dilatancy in foams. The problem is that it's quite small and it's very hard to measure experimentally. It hasn't been measured yet experimentally, so we are still waiting for values of n to compare with our prediction. But it still has been observed qualitatively that if you shear something with a non-homogeneous shear, then the liquid fraction becomes higher in the regions that are highly sheared. So there is some dilatancy. Now if I'm going back to shear bands, I still have to add the effect of the glass plate. So we've seen that this effect is proportional to the speed of the bubble to a given power. This power should be also 1/2 of 2/3, but since it's already 1 everywhere and it apparently doesn't change anything, we'll take 1. And here's what happens. That's the velocity as a function of the position. If you don't have any friction along the glass plate, you find a linear velocity profile. If you increase the friction along the glass plate, you increase the localization of the flow. The shear bands gets narrower and narrower. If you plot the velocity profile in a semi-log plot, you can see that it's roughly exponential in the first layers, but then it's slower than exponential, which is another way to say that it's depends actually on the driving speed, which was what the Leiden group observed. Here you can fit all of these profiles with the solution of the equation that balances the internal drag, so the Herschel-Berkeley drag, with the wall drag here, drag along the plate. this equation even has an analytical solution that's a bit too complicated to be useful, but you can make some very nice simplifications. And in the end, we end up with a prediction of how the width of the shear bands depends on the driving speed. It varies like a power law, and the power is the Herschel-Bulkley index minus the index of the wall friction divided by 1 plus the Herschel-Bulkley index. In general, m is always negative, so the velocity, if you increase the velocity, the shear band becomes narrower, which is what was observed. And there is a case where if the Herschel-Bulkley index is equal to the wall friction index, which is what happens for a monodispersed foam, then there's no dependence in V anymore. And that's why Denin found something independent of V, because he had a monodispersed foam. So the conclusions are that this granular approach is quite a good tool if you want to understand how foams flow in a dynamical regime. We can reproduce the Herschel-Bulkley rheology that is observed experimentally. We can predict the fact that there is a dynamic dilatancy. We can reproduce correctly the shear bands that are formed if you add a glass plate to the 2D foam. And I haven't had time to show you, but you can also model different kinds of flows, like the flow through a constriction of Yann, or the flow around an obstacle. And now the questions that remain are, is this Herschel-Bulkley index of 0.4, 0.5 something completely universal? Because it seems that it doesn't depend on any properties we have except for the polydispersity. And then how can we model and understand the transition from the purely monodispersed case to the completely polydispersed case? Then we don't know where the n, that's the index for the dilatancy, comes from, and we don't know whether or not it's related to the Herschel-Bulkley index. And finally, we would like to know if everything would be the same in 3D, and actually we don't even know whether there are shear bands or not in 3D foams. So thank you for your attention.
Your results for the normal stresses, the power you have there is different from the
Yes.
shear.
Yeah.
Does that mean you have normal stress effects? I think it means that. I'm not exactly sure.
What do you mean?
Well, normal stress effects in which you have anisotropic normal stresses in this direction different. And then it would also mean that the Herschel-Bulkley parameterization is not the right parameterization in 3 dimensions. You would need something more complicated, say a stress tensor that depends on d square, the stretching, square of the stretching tensor.
That's very possible, yeah.
Which is not the case in the Herschel-Bulkley parameterization in 3 dimensions.
The problem of the 3 dimension is that if you want to have a very wet foam, you would need to have very small bubbles, because otherwise, if you have a large sample, all the water would flow down, and you would have liquid fraction that would vary through the sample. That would be very annoying. So if we want to, we have either to get rid of gravity or to have very, very small bubbles to perform experiments in the wet regime in 3D.
Were your experiments made in a Kuwait?
Not ours, but the Debrejas experiments. Yeah, but then the foam is not wet. Or you have to take very small bubbles.
Well, you had this slightly tilted wheel, right?
Or for the rotating drum. Yeah, but we only had 1 layer. If you add more than 10 layers of bubbles, then the water would flow down. So it's very hard to do experimentally.
Yeah. Is it possible to do any of these bubble experiments on curved surfaces? Because a lot of the reason perhaps the monodispersed case is different in 2D is that things can pack extremely well, and if you can do it on a curved surface, then you break up this regular packing.
There are things actually, but static studies, I think Nicola knows about that.
Tim Sandon and Di Meglio have been trying to do this, but apparently it hasn't been very successful.
Because it was
static
structural properties, not flows. I don't know. Yeah, maybe that's.
That might
to
give
break
something
the
more, yeah, to break up the
break, yeah,
crystallization.
yeah. But because in Leiden they've seen that as soon as they introduce very few defects, it changes from the monodispersed regime to the polydispersed one.
Have you tried to push the granular analogy further by plotting the ratio between the shear stress and normal stress?
No, I should. But there's no. We thought it would be easier because there's no solid friction, but actually the viscous friction is not much easier because you don't know what power you should take.